Okay, this is an introduction video to conics and parabolas. So we looked at this slide when we talked about circles, but the definition of a locus is a collection of points that satisfies a specific criteria. So with circles, we talked about a locus is a set of points that are all equidistant from the center. Remember, a circle, if we take a cone or a double cone, a circle is formed by making a line, like kind of a cut across the circle that's parallel to the base of the circle, or of the cone, because the base of the cone is a circle. Today we're going to talk about parabolas. Parabola is formed when you take a line and you make a cross section, and that line is parallel to the side of the cone or the edge of the cone. That type of cross section that's made always creates a parabola. So we're going to look at parabolas. Now parabolas are also something that you looked at in Algebra 2, Algebra 1 with quadratics, but we're going to look at them from a different perspective. A parabola can be defined, I'm going to zoom in a little bit. A parabola can be defined in terms of a single point of focus that's on the inside of the parabola, and a fixed line called the directrix. So in the past, when you have worked with parabolas, you may have worked with, you drew the curve, you got your points, drew the curve. You may have talked about an axis of symmetry going down the middle. Okay, you may have talked about the axis of symmetry. It's just a vertical line going through the vertex. The directrix is always perpendicular to the axis of symmetry. It's called the directrix. It's a horizontal line in this case. It's not always horizontal, but horizontal line in this case perpendicular to the axis of symmetry. It's always perpendicular to the axis of symmetry. So the relationship of the points on the graph, so the collection of points, that locus of points, is given by our definition right here. A parabola is defined as a set of points in a plane whose distance to the focus equals the distance to the directrix. So for example, if I go from the focus straight down to the vertex, okay, the vertex is a point on the parabola. That's 1 unit, whatever my units are here. If I go from the vertex to the directrix, it's exactly 1 unit. Another one I drew, this horizontal component, if these were given as numbers, right, like 0, 2, -2, 2, that's exactly 2 boxes away from this point on the parabola, and this point on the parabola is 2 boxes away from the directrix. So I can pick any point on the parabola and the distance to the focus should equal the distance to the directrix. That's what makes a parabola a parabola. We call this the focus directrix definition. And there's the focus directrix definition of any conic section is its relationship between the directrix and the focus. We don't use that for a circle because we don't have a directrix for a circle. So let's take that definition and actually build an equation out of it. So I have any point on my parabola, so this represents any point on the parabola is going to be x comma y. We're going to define our focus point, F, as 0, p. We use the letter p inside of our equation, and we'll talk about what p is. But right now, I guess we can talk about it. We're saying that p is the distance between the vertex and the focus. So for our purposes here, P is the distance between the vertex and the focus. And you can have a sideways parabola, and so then it's the horizontal distance, but it's still the distance between those 2 points. So if that distance is P from the vertex to the focus, then the distance from the vertex to the directrix is also P, because that's what our definition is. So if I started at, let's say, 0, 0, which is what it looks like on this graph, and I went up P units to get the focus, I'm going to go down P units to get the directrix. So my directrix is at y equals negative P. And then the last point I need here to derive my equation is I need D. Excuse me, D is a point on the directrix. And it's going to have the same x-coordinate as P, which is x. And I know you could say, well, why isn't it negative x? Because we're letting this point P represent any point on the parabola xy. I just happen to draw it to the left. And it's going to have the same y-coordinate as the directrix. So it's going to be x comma negative P. So we're going to use these, and we're going to use the definition, and we're going to create the equation for a parabola. The definition for a parabola says that it's a locus of points that are equidistant from a fixed point, the directrix, or sorry, fixed point, the focus. And so it's the same distance to the fixed point, the focus, and the same distance to the fixed point, the directrix. So those two distances have to be the same. So we're going to say PF, that's the length of segment PF, is equal to PD. That's the length of segment PD. PF, using the distance formula, is going to be the square root of x minus 0 squared plus y minus p squared. That's going to equal PD. PD is just a vertical line, so the distance is going to be y minus negative p. Right? If that was like, if p was at 10 and d was at negative 2, we say the distance between them was 10 minus negative 2, or 12. So this equation is just PF equals PD. That's the definition. Any point P on the parabola is the same distance to the focus, that's PF, as it is to the directrix, that's PD. So if I clean up this left-hand side, I'm going to get the square root of x squared plus y minus p, quantity squared, equals y plus p. I'm going to square both sides. And so on the left-hand side, I have x squared plus quantity, y minus p squared. And on the right-hand side, I have y plus p, quantity squared. Now I'm going to expand both of those parentheses. And so the left-hand side is x squared plus y squared minus 2yp plus p squared. The right-hand side is y squared plus 2yp plus p squared. If I subtract p squared on both sides, that goes away to 0. If I subtract y squared on both sides, that goes away to 0. And so I have x squared minus 2yp equals 2yp. I'm going to add 2yp to both sides. And so I have x squared equals 4yp. And I'm actually going to say 4py. And so you see the y equals x squared part. and you see this 4p. And this is a general equation of a parabola with a vertex at 0, 0. And we'll talk more about that, right? And my first question about that is, what is p and what is 4p? So we already talked about p. We said, what is p? It's the distance between the vertex and the focus. That's how it's defined, which is also the distance between the vertex and the directrix. So how is 4p related to y equals ax squared plus bx plus c? So if I had x squared equals 4py, if I want to relate those, I'm going to put those into the same type of form. So y is going to equal, divide both sides by 4p. So 1 divided by 4p times x squared. So from our standard form of a quadratic equation that we've seen before, the a value is equal to my new 1 over 4p. So the 4p is going to tell you how wide or narrow your parabola is. So p by itself, okay, how far away the vertex is from the focus is going to then indirectly tell you how wide or narrow your parabola is. If I use this same graph and I pick a point, let's say right here, we could figure out the length of that. So this segment I just drew, this green segment, for now, let's just, I don't want to name it anything. Let's call it L, line L. Line L is called the lattice rectum, which is a chord going through the focus. It's not just any chord through the focus, because I could draw another one that ends on the parabola, but it's a chord through the focus that's perpendicular to the axis of symmetry. And the question I have for you is, what would the lattice rectum length equal as a number or as an expression? So you can pause the video and see if you can play with that. Based on the definition, we know that the focus is at P, which means that the directrix is P away. So the distance from the focus to the directrix is 2P. That means that this chord, since I drew it perpendicular, has an endpoint that's 2P away. And the definition of a parabola says that any point on the parabola is the same distance from the directrix as it is from the focus. So that means, I'm going to use my highlighter. That means this section also is 2P, because that's the point to the focus. So the lattice rectum length is 2 of those, which is 4P. So if I'm looking at this equation, y equals x squared, but I have this 4P in front of y, the 4P is actually how wide the parabola is at the focus. How wide the parabola is at the focus. Okay, so here are two. Let's see if I can show both of them. Here are two. Actually, this is the same parabola. This is horizontal. So the screen on the left shows you just the general equation at 0, 0. The screen on the right shows you the equation shifted somewhere else, h comma k. So on the left, we say if our p-value is positive, right, you have x squared equals some positive number y, then it's going to open up. If you have x squared equals some negative number in front of y, it's going to open down. Because if you look at it as y equals 1 over 4px squared, a negative versus a positive there is going to have a reflection. Even though I circled this one and we're kind of thinking about that, we're thinking about it like that because that's what we're used to, but we need to get used to this one. We need to get used to the conic form of a parabola. Now, if I have a shift, right, this is, for example, a shift horizontally by h and vertically by k. On the graph, it looks like it went to the right h and up k. If you shift your vertex by p units, then you have to shift your focus by p units. Or sorry, by k units. Okay, vertical shift of k. Then we have to take that vertical shift and add it to the p-value, even if it's negative, so like negative 2 plus p, or 2 plus p if it's positive. We have to add it to the directrix. The axis of symmetry is going to shift to h. So horizontal directrix, notice they're talking about a horizontal directrix rather than just the y value like x squared. I can also look at these with a vertical directrix. So I can look at y squared equals 4px instead of x squared equals 4py. If the y value is squared, you're going to have a sideways parabola that either opens to the right or opens to the left. And so you'll need to pause your screen and make some notes about that. Your vertex is still hk, but this time if you shift by hk, you know, a horizontal shift is going to affect your focus in your directrix instead of the vertical shift affecting your focus in your directrix. So we are going to spend time in class going through what that means for problems. The very last thing I want to tell you about is called eccentricity. Eccentricity measures how much a conic section varies from being circular. So a circle has an eccentricity of 0 because it is completely circular. It doesn't vary. A parabola varies quite a bit because it doesn't look anything like a circle. Like it's curved, so maybe it looks more like a circle than it does like a line, but you could argue that maybe it doesn't. Okay, so the eccentricity of a parabola is equal to 1. This box right here, the eccentricity of a parabola, is the distance from the focus to any point on a graph divided by the distance from that same point on the graph to the directrix. So like in this diagram, the distance from the focus to the point on the graph is 2 units. The distance from the point on the graph to the directrix is 2 units. And so 2 divided by 2 is 1. We're going to have a bigger or more kind of at the same time general and specific. We're going to have a better definition of eccentricity. And we'll talk more about it when we study ellipses. But I just want you to know that for a parabola, the eccentricity is 1. And I'll show you guys a video or something about eccentricity and stuff later. But eccentricity of a parabola is 1. And that's what you need to know before you come to class.